Okay, this is a fifth video, and like before, this is a problem set I'm giving to my class. If you're not in my class, what you would want to do is just copy the screen while it's blank. Okay, that means before I start marking it up, messing it up for you. Okay, and again, the idea here is that you do as much as you can on your own, and you only use what's appearing on the video when you actually need to. All right? Okay, so these four problems that are on this video are all going to be mechanism problems. Let's look at some of the essential features of mechanism problems. What we have to do is figure out how to get from A to B using only things in the reaction equation, or things that are generated. Okay, so that balanced equation there would have water in it, so we could consider also using water at any point in the mechanism for that reaction there as well. Okay, all right. So what type of reaction is this? This is two carbonyl groups coming together, making a new CC bond right there. This is bases causing it to occur. This is obviously the aldol condensation. It's forming a ring, so that means it's probably more than likely intramolecular. Okay, the product of an aldol condensation is an alpha-beta unsaturated carbonyl. What does this mean? Okay, it means generally the aldol condensation, alpha carbon. This is the carbon that was deprotonated. Beta carbon is the carbon that provides the carbonyl group that reacts with the anion from the alpha carbon. Okay? All right, so let's look at this one. If we look at all the hydrogens on alpha carbons, there's 6 of them. Okay? But we can clearly see that if we look at that description there, it's one of these hydrogens being removed that gets us to the product. All right, so let's remove that. We use OH minus as the base. I'm going to draw carbanions as intermediates rather than enolates because the drawings are a little bit clearer when you do that. Enolates are really what they are, but this sort of tells you exactly what's happening a little bit more clearly. All right, so anionic carbon has to connect with an electrophile. Here's the electrophile, the C double bond O group. Does that. This makes our 6-membered ring. Okay. That gives us this. We're going to protonate it to get our first product. First product is the beta hydroxy carbonyl compound. Okay. And we would get that if we had only run the reaction at just 25 degrees or at room temperature instead of at 80 degrees. However, at 80 degrees, another process takes over. That's this one. Okay, so this makes another anion. And this produces the final product right here. Okay, so that's the simplest possible mechanism I can write. It transforms starting material into the product. It uses only the things that are in the reaction equation. And this is kind of what you're shooting for when you see that the problem is asking you to write a mechanism. Okay, let me just say another thing about this reaction. I went right to the answer because I know what the aldol condensation does. But had we not known that, and we're trying to think of the answer just from reactivity principles, we could have figured it out. It would have taken a little bit longer. But what would have caused it to be longer would be all these sideshows, okay? Sideshows mean things that are happening, but they don't lead anywhere. Sideshow number one. Deprotonating other alpha hydrogens. Yes, this is happening. But let's imagine that I deprotonate right here. If I deprotonate this and add there, I'm going to get a 4-membered ring. That's not great. Even if I do that, it's probably going to reverse. The equilibrium is going to favor the open chain compound because of the angle strain. So that's happening, but it doesn't lead anywhere. Sideshow number 2, hydrate hemiacetal formation. This is happening as well, okay? All right, so any aldehyde or ketone, if reacting with base or alkoxide, and followed by deprotonation, is forming a hydrate or a hemiacetal. That's occurring as well, but it's not leading anywhere. Once you form the hydrate or the hemiacetal, you realize that there's nothing you can do with it. Okay? So that's a feature of a lot of mechanism problems, that you're going to go down a lot of dead-end pathways before you find the pathway that goes forward. Okay? All right, so I already knew this because we've studied the aldol condensation extensively and know those are the characteristics to look for right there. Okay, let's look at this next one. This is also shows 2 C double bond O compounds and a new CC bond. This is obviously a condensation reaction of some sort. This is since one's a ketone, one's an ester, this is a mixed aldol-claisen or an aldol-claisen hybrid. Okay, so we're looking for alpha hydrogens. There's the only alpha hydrogens we have. This compound drawn out is this. There are no alpha hydrogens. Okay, remember that the hydrogen directly attached to the carbonyl group in a formate ester or an aldehyde is not an acidic proton. You cannot write a resonance structure for the anion that you draw right there. Okay, so it's only the alpha hydrogens at the alpha carbon, which we just casually call alpha hydrogens, that can form a stabilized anion. Okay, all right, so OET minus is the base. Okay, this is how it starts. Okay, so this is the typically the first step of any of these condensation reactions, deprotonating at the alpha position somewhere, and that's the only alpha position that we have. Okay, clearly there's a union of the ester part, so we're going to add this to the ester, and the only way that we can, by adding to the carbonyl group. Okay, by the way, another point I want to stress with writing mechanisms. Bond line diagrams, they're your enemy, okay? Just, it's best to not draw the bond line diagrams in the vicinity of where things are happening in the mechanism, okay? Try to, in the carbons that are directly being attacked or doing the attacking, try to draw the hydrogens in right at the point of attack, like I've done here. Okay, so I'm drawing all the hydrogens and being very careful to do that. All right, so that's what we have there. Okay, this course is going to now kick out that. And this is going to give us almost the product, okay? This is a very acidic proton. pKa is about 10 for hydrogen that's alpha to 2 ketone or aldehyde carbonyl groups, so it's going to be impossible to stop this deprotonation step right here. Okay, at this point, the aldehyde, being the less stable carbonyl group, is the one that's more likely to form the enolate. Okay, so this is our product, and it has a sodium counterion. It's probably the double bond chemistry that you see there is probably showing some sort of association, covalent association to sodium. Okay, it's predominantly an ionic bond, but there's a lot of covalent character, and that's probably why you're seeing the, I guess, we'll call this the Z-alkene geometry there, because there's a covalent association to both oxygens with the sodium. Okay, all right, let's look at this one. All right, what would we do here? There are a lot of things that we could do, things that you could do. All right, no alpha hydrogens, so we don't deprotonate anything. Okay, other things we can do. Can add ethoxide to a C double bond O. What else can we do? We can add ethoxide via a Michael addition. All right, lots of things can happen here. Okay, all right, so it looks like if you compare these two compounds, it looks like there's some sort of substitution that's occurred at that carbonyl group. So let's sort of go with that as being the thing that we want to do. All right, so how would it substitute there? It would do this via nucleophilic acyl substitution. We add something, then kick something else out. Okay, so let's just explore that idea. All right. Okay. Methyl group. Methyl group. What can we kick out? We can kick out ethoxide. That's just the reverse of what we just did. We can kick out this. This gives us an anion at sp2 carbon, for which we can't write any resonance structures. The only thing that's good to kick out is probably this group here, which would give us enolate. All right, so let's kick that out. Okay. All right, so that gives us this, which remember might be better represented as an enolate. Here the enolate is actually what we should gravitate to. All right, there's free rotation around, well, mostly free rotation around that CC bond, since it's a sigma bond, not a double bond, it's just a single bond. Okay, so here we go. There we go, right there. That gives us that. This is actually starting to look like the final product. Okay, all right. Okay, so now we can see that this is now the product of a nucleophilic acyl substitution this way, right? So okay, so that gives us this, and now we can kick out ethoxide. This means ethoxide is just a catalyst here, not really consumed by the reaction. And that would give us our product. So there's actually a pretty good mechanism. There are a lot of other things that could happen here. You could have added to the other carbonyl group. That could happen. What I think is happening here is that we have a powerful resonance interaction right here that makes this the more stable compound, okay, as opposed to attacking the other carbonyl group. And that's more than likely what's occurring in this case. All right, let's look at the reaction here. LDA. Very strong base. It's kind of hindered. It doesn't really function very well as a nucleophile. So what it does best is it removes protons. All right, let's look at all the hydrogens that could possibly be removed. We find that only these hydrogens right here are alpha to a carbonyl group. Remember, this is not an acidic hydrogen, so we can't remove that with a base. All right, so our first step, the only logical first step, is that diisopropylamide anion does that. Okay, again, I'm going to just draw the carbanion form because that gets us to the answer quicker. Okay, all right, so there's our nucleophile. It now needs to add to something. Here's the other partner. Okay, so let's go ahead and just add that. Okay, we have the hydrogen. Okay, so this looks like the conditions for the for the directed aldol too, but why don't we just protonate oxygen? We could do that, but a very fast reaction is ideally set up to happen here. Recall that a couple of chapters ago we looked at how to make epoxides by deprotonating halohydrins, right? Okay, so once we get here, we actually have this reaction in place. All right, so this alkoxide cannot help but do a very rapid intramolecular SN2, and that gives us our final product. Right? And this is called the Darzens condensation. Okay. All right. So because of the presence of the chlorine, instead of that alkoxide here waiting around to get a proton, it has a very rapid intramolecular SN2 reaction available to it, and that's the fastest thing that occurs. Also, when under these conditions, there's not a lot of things around to protonate that alkoxide. Okay, recognize that the side product of the first step was actually diisopropylamine, which is not a very good proton source. Its pKa is about 33, so it's not very good at protonating things. Okay. The remaining problems are synthesis problems, and I'm going to put those in a separate video.